the programming language that we're developing for verified low-level systems programming. So we would like Pancake to be used for writing low-level system programs like device drivers, and we want to use a Pancake framework to verify those programs. And also by verified, we also mean that we have a verified compiler, and it's developed on top of SL4. So the primary target for us is device drivers because we consider that device drivers are the major source of bugs for OS. And we also think that if we can verify device drivers, it should be also possible to verify other OS components as well. And in terms of design goals, as Gernot's slogan goes, so radical simplicity is what we want. So simple and easy syntax that is easy to use and learn for the typical system programmers. And we also want Pancake to have simple and easy formal semantics for making verification easy and possible. We also aim for light footprint with no runtime, no GC, so for the purpose of performance and also verifiability. So in terms of the bigger picture, so this is the diagram that you have seen several times during this talk. So it was in Darren's and Gernot's talk. Pancake aims to contribute around this level, so like lower part of Lion's OS, obviously. The project has been going on for a few years now, so 2 universities from Australia, UNSW and ANU, and 2 from Sweden, so Chalmers University and Gothenburg University are participating, and TII and a few other funding resources are helping us in terms of funding. So big thanks to them. In terms of people, we have a bunch of people working on the project now and past. Credit to all of them. In particular, Johannes, second from the bottom here, has been a TS member till this July and was leading the project, so big thanks to him. All right, let's have a quick look at the Pancake code. Stare for a few seconds, and if you think that this doesn't look so different from C, then that's what we want. We really want typical sort of system programmers who are normally writing in C to find Pancake easy to adapt and get using actually quite quickly. But of course, there are differences as well. Well, firstly, Pancake doesn't have types. Everything is machine word in memory, and you'll be dealing with that. And the rationale for that is that if we are going to verify the programs in Pancakes on Serial Improver, its property, then types, we think the types, what type provides isn't not that much useful, so well, we could actually do without. And that goes for the simplicity principle as well. And Pancake has much simpler semantics than C, and it fits like a few hundred lines of whole for formal definition, and practically nothing is undefined, as opposed to, well, that's a big difference for C, and that's important for verification. And we have a few other sort of simplifying design decisions, like no dynamic allocation, and so on as well. And of course, Pancake has a verified compiler, which is a big thing. So the guarantee that you get is that from the level of AST down to ISA, we have the semantic equality. And this is due to the KQML that Pancake compiler is derived from. So I'm going to talk a little bit about KQML now. So you can say Pancake is an offspring of KQML, or KKML people would say that Pancake is part of KKML ecosystem. So KKML itself is a functional programming language, and that is a bit too high level for writing systems software. But it has nice optimizing compiler with bootstrapped binary. So that diagram there is a compilation stack of Pancake. So you have Pancake AST at the top and generated assembly ISA at the bottom, and each blobs there represents intermediate representations. And arrows on the side, each of that is the compiler sort of translation phases. So if you have many transformations that are proven equal, so before and after the transition, the semantics are preserved. And that's how its correctness is proved. Yes, in that sense. Then, yeah, and all of these are developed on Hall 4, and that's why Pancake is also developed on Hall 4. So how Pancake connects to this is the next step. So there are a few existing work that compiles down to KKML. So there are some different languages there, and KKML has a synthesizer that translates a whole formula into KKML program, and that's kind of relevant because this is used for bootstrapping. But all of these compiles down to KKML, which is too high level for Pancake. So Pancake compiles into middle point of KKML stack, which is specifically called word lang. So that's the intermediate representation that Pancake compiles to. So that's kind of unique. And if you put these two together, the compiler stack now looks like this. So the top part on this side is the Pancake stack, and it sort of merges into the second half of the KKML compiler stack. So Pancake itself now has a proven correct compiler from the end to end, so AST down to the bottom. And merging is kind of interesting work that we did. And so this merging point, word lang, is quite low level, so everything is word. And somewhere just before word lang, KKML's garbage collection facility is introduced, and it's sort of done from that point on. So the interesting experience of this merging, sort of putting things together, is that Pancake doesn't use garbage collection, so all the garbage collection facility at the bottom are sort of switched off or excluded for Pancake. And we also, after doing this compiler proof, we extended Pancake with a shared memory feature, so the ability to read and write the external memory, mainly to enable memory mapped I/O. And so that was done for Pancake, and that meant that lower half part of the KKML compiler also needed to be extended with that capability, but KKML itself doesn't use that, so we have sort of switched on and off features for both Pancake and KKML. That's kind of interesting situation. So the two kind of coexist like this. But yeah, Pancake is still a sibling of, offspring of KKML in a sense that the binary for Pancake is available as part of KKML. So you can invoke Pancake as a KKML option like this. And if you go to KKML website, you can grab the binary, KKML binary. So please do have a try if any of you are interested. So that's how things are. That's KKML. So let's now have a quick look at performance of Pancake. So we've been working on this from sometime this year, and we made good progress relatively short time. This is Ethernet driver returning a comparison between C version and Pancake version. Pancake version calls out to microkit via FFI to C, so that's definitely an extra overhead as well. We are around, yes, so the 28% overhead on this side. But we are still working on it, and we are quite confident that further improvement is possible, so please wait and see how we will do. And so that's that. The major work, things that we've been doing is to extending Pancake to use less of C, so like shared memory feature that I mentioned. Previously, we had to call out to C to be able to do that, but now that Pancake has its own facility to do that, we don't need to call out to C, and that was a major good improvement for the performance. Okay. And moving on to more onto the verification side, quick look at the semantics. So Pancake has two different semantics defined for now. So first one is functional big step semantics, which is essentially the same as KQML semantics. And this is used for proving the compiler correctness. And so this is functional, as it say. So this is primarily a deterministic thing. And in terms of verifying device driver, it is sort of, there are limitations that we consider needs extending. So firstly, so this is a deterministic structure. So modeling interaction with external environment, which we will need for device driver verification, it is quite fiddly to handle. So the way the current semantics deal with that is by including Oracle to model the FFI in the state, and that is consumed as the evaluation goes on. So that's one situation. And also this semantics is, the functional big step semantics is, is the finite structure. So it's not really convenient for expressing divergent situations, so where you have infinite I/O sequence that you want to express, it's expressed as the limit of the clock value that state carries around. On the other hand, the second semantics that we have defined for Pancake is using a new co-inductive structure developed by Shear and other people quite recently. And this captures the interaction and continuation as a sort of data type. And it gives us the direct interpretation, representation of divergent situations, and the evaluated semantics can combined with any oracles, so that is more generic in general to express those situations. And we have proved soundness for this semantics, and completeness is on its way. Right, so that's the tools that, well, semantic tools that we've got. And in terms of how we want to proceed with driver verification, we have few things on the menu. So as a target, we started experiment with some virtualizer, and we've also done a few tests with experiments on serial driver, and many people currently are working on looking into Ethernet driver. And in terms of what to use for verification, so we have a few people working aiming to use SMT, so push-down verification, by means of translating Pancake to Viper. Viper is the input language for various SMT system that is currently developed at ETH. And we are trying to write the translator from Pancake to Viper and also verify that translation as well. And in terms of, on top of whole 4, we have 2 semantics, as I explained, and those combined with direct verification, the smaller experiments, or whole logic to do the manual verification. We also have just started a project of defining the decompilation for Pancake, and that means that we will have a translation from whole Pancake program to whole 4 formula with certification of correctness, so that we will be able to prove the property of those programs written in Pancake. Yeah. So that's the broader plan, and that's all from me. Thanks.
Thanks, Miki. Any questions?
So you said there is almost no undefined behavior in Pancake. What would be an example of undefined behavior?
Yeah, that's probably we're trying to be too precise, perhaps. So the semantics has various error cases, and of course we're not being too precise about those error cases, and that was mostly what was in our mind when we were thinking about saying that. So that's how it's happened.
Any others? Nick has one.
If I have a Pancake program with a performance critical part and I'm not happy with the code gen, can I drop down to a lower level in the stack, like I can with inline assembly in C, for example? I mean, it sounds like that probably wouldn't work super well with the higher level proof techniques you showed on the other slide, but does Pancake itself support that? Like inline, whatever lower levels you have there, or maybe even assembly?
Pancake compiles directly down to binary. There's no intermediate representation that's accessible. It's inside the compiler, of course, but it doesn't get exported. If you need to perform operations that are not presently available in Pancake, you need to do a foreign function call, which for the drivers initially we had a lot, and then things get integrated into the language bit by bit. Now all the proper driver code except the cache management operations are all inside Pancake. Those still need FFIs, but that will go away soon as well.